Hello, my name is Mihai Fieraru, and here I present our work, REMIPS, physically consistent 3D reconstruction of multiple interacting people under weak supervision. Given a monocular image, our goal is to efficiently reconstruct all humans in the scene, irrespective of their number. Our method predicts physically plausible 3D reconstructions, even in challenging scenes where people interact with each other. All predictions reside in a common 3D coordinate system, avoid self-collisions and interpenetrations, and preserve their expressiveness in terms of self-contact and interaction contact. Since 3D ground truth is very expensive to collect, we eliminate it completely from our training pipeline. A couple of multi-person reconstruction methods have been proposed lately. While some of them are optimization-based, others are based on learning. When trained, they are either top-down or bottom-up. Here we propose a top-down method and use the GHUM statistical body model to represent the humans. To reconstruct contact, recent works have proposed learning either the interaction contact between people or the self-contact. In our work, we bypass predicting contact signatures and instead directly learn the 3D reconstruction using contact annotations. Several methods have also been proposed for avoiding self-collisions and interpenetrations. They are either too slow for learning, or use rough approximations of the human surface or of the loss functions, so we propose a unified collision model without such weaknesses. Here is an overview of REMIPS. Given a monocular image, we first use an off-the-shelf person detector to locate each person in a scene. Our novel idea is to treat each detected person as one token of a transformer network. We represent a person token by its bounding box coordinates and an initial default GHUM state. On a separate branch, starting from the image, we run a backbone convolutional neural network architecture to extract spatial image features. Drawing inspiration from vision transformers, we also treat spatial image features as tokens. While image feature tokens require positional encoding to keep track of their order, the person tokens are treated as an unordered set. To concatenate the two sequence representations, we linearly project each of them to a common dimension space. Next, we iteratively refine the tokens through a single transformer encoder layer for a number of L stages. At the end of each stage, we collect the transformed representation for the person tokens and apply an MLP to regress the residual GHUM state estimates. Our final estimation is given by the weighted sum of all the residual state updates and the initial GHUM state. Note that while in training we use the fixed number of 16 person tokens for batching purposes, during inference our network can use as many person tokens as the person detector outputs. In practice, when going from 1 person to 32 persons, the inference speed increases insignificantly by around 10%. We train the proposed system in a weakly supervised manner with a sum of collision losses, contact losses, a depth ordering loss, a key point alignment loss, and pose and shape regularizations. Here we show how each collision and contact loss used in training positively impact the reconstruction error on Chi3D, the challenging dataset of interacting humans. We quantify the joint error and the vertex error. I will now describe our proposed unified framework to handle both self-collisions and interpenetration collisions. To reduce the complexity introduced by the high number of vertices of the GHUM topology, we create FUM by applying decimation operators to GHUM. With only 5% of its vertices, the nearest neighbor distance from FUM to GHUM is a negligible 2.8 millimeters. The FUM mesh can be easily reposed and reshaped with respect to the underlying GHUM mesh it approximates. We therefore use FUM to test whether 3D points are inside or outside a closed mesh using the generalized winding number test, which is quadratic in the number of vertices. For self-collisions, we push outside each vertex found inside its own closed mesh. For interpenetrations, we push outside vertices found inside other closed meshes. We compare the runtime of our self-collision loss with the one proposed in Simplify X based on bounding volume hierarchies. Our loss is faster and penalizes all vertices inside the mesh, not only those at the border. To preserve contact expressiveness, we also train using losses that minimize the distance between vertices annotated to be in contact. We do this for both self-contact and for interaction contact. We outperformed the current state-of-the-art methods on the panoptic dataset in terms of mean per joint position error, even though no 3D supervision is used during training. Similarly, we outperformed the state-of-the-art on the Chi3D dataset in terms of joint, vertex, and translation errors. Here we show visual results on the Chi3D dataset. In the middle, we show the reconstructions when the contact and collision losses are not used during training. On the right, we show the reconstructions when training with all losses. As you can see, contact is established and collisions are avoided. Now, we show visual results on the Open Images dataset. REMIPS can reconstruct any number of people in a scene. Predictions are correctly positioned in the same coordinate system. They are accurate in terms of pose and shape and are physically coherent. Contact is reconstructed, and any type of collisions are avoided. To conclude, we introduce an end-to-end transformer model for 3D pose and shape reconstruction of multiple interacting people, which we call REMIPS. We propose new models of self-collision and interpenetration based on reduced resolution and winding numbers. The method is weakly supervised, no 3D ground truth being used to train the system, and we achieve state-of-the-art results in challenging benchmarks with impressive visual results. Thank you for your attention.